Good evening and thank you for joining us. Our talk for today is entitled Off-Grid Systems for Energy Poverty Alleviation. We have two presenters. We have the chairman of the IEEE South Africa section and our distinguished lecturer, Professor Henry Louie. Firstly, my name is Pat Naidoo and I'm your moderator for this evening. Housekeeping issues. Attendees are reminded to ensure the volume is turned up on their device. Also ensure you have a stable internet connection. You'll enjoy the session. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. And this is located on the right-hand side of your screen. The chat function is reserved for the organizers and the panelists. However, you have the questions panel. You could ask questions using the questions panel. A recording of the presentation will be made available on the SAIEE YouTube channel, the SAIEE TV. This will also be available on the SAIEE website under the events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so please check as often as possible. You'll be able to source the presentation. You'll be issued with a certificate of attendance once we have the CPD validation details from EXA. So thank you, colleagues, and thank you for joining us this evening. Our first presenter is Dr. David Oyedokun. David is Senior Lecturer at the University of Cape Town. So David's joining us from Cape Town this afternoon. And David is Chairman of the IEEE South Africa section. He holds a PhD in electrical engineering from the University of Cape Town. Yeah, David has served on many of the IEEE committees. He has this deep passion for community-based outreach projects. These research interests are in power system stability, geomagnetically induced currents, and renewable energy. So I'm going to pass you over to David, who's going to welcome you. And as host for this evening, he will give you a short presentation. Thank you, and over to David. I'm going to hand you now to David. There you are, David. Thank you.
Thank you very much, Prof. Naidoo, and good day to everyone else, and thanks for joining us. The topic for our discussion this evening is on off-grid systems for energy poverty alleviation, and I'll take you through a short presentation. But before I go into the full details, I would like to just highlight a bit about the IEEE. Our mission is to foster technological innovation and excellence for the benefit of humanity. And as part of our vision, we seek to be recognized globally for contributions of technology and of technical professionals in improving global conditions. And this includes conditions in South Africa, Sub-Saharan Africa, the whole of the continent, and the rest of the world, which forms the basis of our discussion this evening. IEEE South Africa section is over 40 years old. It has about 13 local chapters, just under 30 technical societies and councils. It has close to 20 units, and it has presence in about 7 of the universities within South Africa. We boast of 1,000 odd members, and since 1977, the section has been able to attract a number of global awards. And the question really is, would like you to get involved, and what would you like to achieve with the IEEE? We understand that the Engineering Council of South Africa, EXA, relies on institutes such as the South African Institute of Electrical Engineers, as well as the IEEE, to deliver programs towards continuous professional development. And that forms part of the objective of the webinar we're hosting this evening in collaboration with SAIEE, the SAIEE PES, Southern African Power Pool, and the rest of our partners. The subject matter of this webinar is of critical importance to the nation, and I'd like to make reference to the Constitutional Court judgment on the 4th of October, the year 2000, the cases referenced. And the case was between the government of the Republic of South Africa, the Western Cape government, and a few other parties versus Irene Grootbloem and others. Looking at section 37 of that judgment, we see emphasis by the judge on the state's obligation to provide adequate housing, including access to electricity. Access to electricity was further contemplated and well outlined in the Electricity Act of 1987, Act 41. And the clause there really stipulates clearly, clause 10, that every licensee shall up to the limit, if any, of electricity which he may generate or supply, in terms of the license, supply electricity within the area of supply as mentioned in his license. And the point of reference here is every applicant who is in a position to make satisfactory arrangements of payment. So in essence, we're saying that access to electricity was provided for in this act. This was further contemplated as well in the Electricity Regulation Act of 2006. And if you look at clause 22 there, it really speaks to the provision of access to electricity. So while electricity itself may not be a right, but access to it through which we get energy becomes very fundamental to human rights in South Africa and in most countries around the world. This was supported, of course, by the Constitutional Court judgment. So energy, just loosely defining it as power drawn over a period of time, really requires the basic infrastructure, which traditionally would refer to as the main grid, which provides access. Having said that, there are quite a number of realities, and a few of those will include the geographical size of the country, the location of urban and rural areas, the structure of the main grid as we know it, which was built over a number of decades to what it is today. That notwithstanding, there are grid infrastructure projects that are embarked on by the power utility, competing use of existing resources, be it financial and manpower, as well as priorities of the government of the day. In a recent publication that was authored by the Department of Energy, it was mentioned that 90% of the households will be connected to the national grid by 2025, and 7% will use quality off-grid options by 2025. So the target at the time, I believe this was around about 2011, was that by 2025, 97% of the households in South Africa will be grid connected. If we look into the details further, we see that about 31% of the South African population lives in rural areas of the country. And in these areas, more than 60% of the households have no access to electricity. The consumption levels of rural customers remain low, and capital recovery costs have always come into the picture when these discussions come to the fore. In addition to that, we acknowledge that there are quite a number of opportunities that are dependent on energy, and that includes access to quality, worldwide, standard education, business and entrepreneurship, access to good medical health and basic health services, as well as agriculture and the preservation of fresh produce to leverage off the harvests from small-scale and subsistence farmers. So within the context of our webinar, which my colleague, Prof. Louie, will adequately take us through, there are three main keywords, which is main grid, off-grid, and energy poverty, which we will elaborate on in great detail. Mini grids, otherwise called microgrids, depending on your definition, does not really have one holistic definition, but in general, whenever mini grids or microgrids are defined, we talk about an off-grid scenario. It's relatively small scale comprise electricity generators. The scope relatively compared to the main grid is also smaller. It may include energy storage, and generally it consists of renewable energy, and in some cases non-renewable energy based on the scenario at play. Within the discussion of off-grid provision of electricity, there's been a number of debates over the last 10 years, and I just would like to pull this case out, the case of Rwanda, that engaged on an expansion project in terms of grid electrification, an investigation of whether or not it did contribute to economic development in the near term. In this particular case in Rwanda that was reported in the literature, after about 3.5 years to 4 years, it was reported that the quantity of electricity consumption remained low, and there was weak evidence for the impacts of this electricity expansion program to poverty indicators such as income, health, and education. While I don't completely agree with this, I would like to highlight that a holistic approach is needed to drive those indicators. Access to electricity, allowing users to use energy is not a silver bullet, but if the external supplementary economic drivers are not given the attention they deserve, then the whole objective of the project will be called into question. At this point, I would like to hand over to Prof. Pat Naidoo, who will introduce the keynote speaker of the evening, and he will take us through a number of fantastic case studies that he has worked on personally within sub-Saharan Africa. Thank you.
Thank you, David. Thank you for that. I'll take back the screen. Thank you. Thank you, colleagues, and I'm going to introduce Professor Henry Louie. I would also like to share with you that this is an IEEE South Africa section event and is co-hosted by the South African Institute of Electrical Engineers, SAIEE Southern Africa, and the Southern African Power Pool. I did send a message to my colleagues in Southern African Power Pool, and in particular to my colleagues in Zambia, ZESCO, to listen in this evening, so they all are there. So welcome to my colleagues from Southern African Power Pool, and in particular Zambia and ZESCO colleagues, as Dr. Henry is part of the family. Dr. Henry received his bachelor's degree from Kettering University, his master's from Illinois, and his PhD from Washington. He's currently the professor in the Department of Electrical and Computer Engineering at Seattle University. In 2015, Dr. Louie was Fulbright Scholar to Copperbelt University in Kitwe, Zambia. He's the president and co-founder of Kilowatts for Humanity, a non-profit organization providing off-grid electricity access and business opportunities in sub-Saharan Africa. Dr. Louie is an associate editor for Energy for Sustainable Development and is a founding member of the IEEE PES Working Group on Sustainable Energy Systems for Developing Communities. Dr. Louie is recognized as an IEEE Distinguished Lecturer for his expertise on energy poverty. The senior member of IEEE, and he has served as Vice President of Membership and Image at Large of the IEEE Power Energy Society. So welcome to Dr. Louie. He's coming in for joining us from Nebraska in the United States. I'm going to hand you over to Henry. Thank you, Henry, and best wishes. There we go.
All right. Let me just get my screen set up here. And I trust that you...
Thank you. Yes, we've got you. Go to slide mode. Thank you.
Okay, here we go. So it's an honor to be speaking to so many of you. As Pat had said, I'm in Nebraska on my wife's family farm here in the United States, trying to get away from COVID the best we can. I think David's introduction was very well suited for what I'm going to be talking about, which is off-grid systems for energy poverty alleviation. And in particular, the observation that providing electricity in and of itself isn't a panacea for poverty itself. There has to be an intentional coupling with electricity access to really improve people's lives. So I'll skip through this since I was already introduced. I do want to mention that if you're really interested in off-grid systems, you can check out my website for more in-depth slides. And I also have a book that I wrote, which is available on Springer, and also you can get it on Amazon and through other book and ebook providers, I'm sure. So
sorry, Henry, go full slideshow. Sorry, thank you.
Is this better? Are you able to see a full?
Okay.
Is this working for you?
No, not yet. Just press slideshow and then it should be okay.
Let's see.
No, it's right at the bottom, slideshow, just slideshow, right at the bottom. That's the one, first class. Thank you, over to you.
Okay. I hope this is better. Let me briefly talk about some of the projects that I've been involved in. These are different electricity access programs that I've worked on through Kilowatts for Humanity, and I will be talking about a couple of these towards the end of my presentation. But I want to show you some pictures just to give you an idea or a reference point of the types of systems that I personally have worked on. These are off-grid systems in different parts of sub-Saharan Africa. Really, Kenya and Zambia is where I focused. And we usually do what's called an energy kiosk model, where we're not providing electricity to an entire village. In fact, that's a pretty rare type of program to do anyway. But we're really using solar panels and maybe wind to provide electricity to a building or maybe a few buildings, and we use that electricity to spur local businesses. So it becomes a focal point for that community and their electricity needs. So the systems are much larger than you would normally put on, say, a single house, but we're also not powering dozens of households. We're powering business centers. We would call them maybe a strip mall here in the United States. So here's just a couple of examples of them. The top one is in Kenya, the bottom one is in Philibaba, Zambia. And over the years, these have grown in size and scale. The top one in this slide you can see is in Chalogwa, and it was actually built out of a repurposed shipping container, as you can see. And in 2017, there was another installation we did in southern Zambia in the community of Minyama. And then just about a year ago, we did another installation in Cheba, Zambia. And we actually have another project that we're doing right now in Kinchomba. And I'll be talking about Cheba and Kinchomba to give you an idea of the process in implementing one of these off-grid systems. But to start, let's talk about energy poverty. So a simple definition of energy poverty is it's the lack of access to modern fuels. And by modern fuels, we typically mean electricity and maybe propane and natural gas. The most recent statistics show that almost 3 billion people rely on solid biomass for their cooking and heating needs. So not quite half of the population of the world, but a very large portion are still using wood or charcoal for heating and cooking. When it comes to electricity access, it's close to 800 million people. Now, this is, again, quite a few people, but that number has actually been decreasing. Just a few years ago, it was over 1 billion. So progress is being made. Those of us that suffer from energy poverty tend to consume low amounts of energy overall. We tend to rely on human and animal power for mechanical tasks instead of motors. And a considerable amount of time is dedicated to procuring and processing fuel. So some research has shown that anywhere between 4 and 20 hours a week are devoted towards gathering fuel for a household, gathering wood. And it's usually done by women and girls. And you can just imagine that the work or the opportunity cost of doing that, not being able to be in school, for example, or not being able to socialize and play with other children. And the energy impoverished often spend a large portion of their income on fuel. They might spend up to 30% of their income on fuel rather than maybe the 5% that people in communities or countries that don't suffer from energy poverty might spend. So it's really an impressive affliction to have, is energy poverty. Now, we care about energy poverty for a few reasons, and I think this figure captures it. So what we have here on the x-axis is the per person energy use per year, and on the y-axis is the Human Development Index. And what the Human Development Index is, it's a number usually between 0 and 1 that the United Nations came up with, and it tries to quantify in a single number the development or well-being of a community or country. And it takes into account really 3 things, and those 3 things are health, education, and income. So it has different indicators for these 3 broad categories, and it rolls them up into a number. And on my screen, you can see that I've plotted it for several different countries. And you see that countries that have low energy use per person generally have low human development indices. And that as we increase access to electricity or consume more, we see higher human development indices. And so what this tells us is that when we give people access to energy, they usually will reinvest that energy in ways that help their health, their education, or their income. And this isn't just conjecture. If we look at, say, China, if we went back, say, 30 years ago, China's Human Development Index and energy use was really quite low, and now it is moving rapidly up the curve here. The other thing that we note about this chart is that even a small amount of energy can have a significant, is associated with a significant increase in Human Development Index, at least for countries that are on the low end of the curve. So South Sudan or Haiti or Niger, if their per person consumption increased, even by a modest amount, we'd expect that to improve their Human Development Index substantially. Whereas a country like, say, the United States, if we increased our per person energy use, we probably wouldn't see a meaningful increase in our Human Development Index. So there's a saturation that occurs. Now, those almost 800 million people without access to electricity primarily now live in sub-Saharan Africa, where there's over 500 million people without access to electricity. We also have people in South Asia, a lot in India, for example, that don't have access to electricity. And I always think it's helpful to remind at least my audiences in the United States that even within the United States, we have pockets of people that don't have access to grid-connected electricity, primarily in very rural areas and in some of our reservations that we have here. So the typical method that we use to measure electricity access is the electrification rate, and it's simply the number of people whose house is connected to the national grid divided by the total population. So this is, like many metrics, imperfect because there are certainly people living off grid that have better access than people that are connected to the grid. As you know, if you're listening in South Africa or Zambia, you're probably familiar with load shedding, and just because you have a power connection to the grid, a mains connection, doesn't mean you actually have high quality electricity. But nonetheless, the electrification rate is a straightforward way of measuring and comparing electrification in different countries. And so the plot on the left shows that the electrification rate has increased rather steadily over time, and is now somewhere around 90%, but it's uneven. And you can see on the plot on the right that there are some countries that have very, very low electrification rates, around 10% for Burundi and Chad. And still, there are many, many countries that have very, very low electrification rates. So even if globally we are reaching 90% and even higher in the coming years, there's still going to be pockets of people and even whole countries that have very low electrification rates. Now, globally, if we look at our global consumption per person, we've increased our consumption by about 260% in the last 40 years or so. And that's an amazing increase per person. So we've more than doubled it per person. But because our population has also grown, our total consumption as a species has gone up by over 500%. So you could see this increase over time. Now, much like electricity access, our consumption hasn't been uniform across countries and regions. This is a fun little game where I've plotted the per person electrical consumption for 4 different regions: China, India, Sub-Saharan Africa, and the United States. And let's take a moment to touch your computer screen or try to figure out which region or country goes along with which plot. And you should pay attention then to not only the shape of the curve, but the scaling of the y-axis here to make your guess. And I'll give you just a moment to try to figure out which of these belongs to China, which belongs to India, which belongs to Sub-Saharan Africa, and which belongs to the United States. Okay, do you have your answers? Okay, here we go. So I think most people can pick out China and India pretty quickly. We have this notion of rapid industrialization in China and India, and you can tell them apart based upon the scale. China's electrical consumption per person is much higher than that of India. So we see those two have these upward trajectories because they're rapidly industrializing countries. And then we look at Sub-Saharan Africa and the United States, and these have actually similar looking shapes to them, but the scale, of course, is very, very different, with the United States being what I would say overconsumers of energy. But let's look at the United States first. So throughout the 1970s, 80s, and 90s, we saw a growth in our per person electrical consumption as our economies grew. And then right around 2000, we started to see it to stabilize. In other words, we weren't consuming more and more electricity per person. And so why was that? Or why is that? Well, I think there's a lot of reasons. We have more energy efficient technologies that we use, like LED lights. Our grid codes or our housing codes are now making us be more energy efficient. We've taken a lot of our heavy manufacturing and we've moved it outside of our borders, so it appears on some other countries' consumption list. So those are some of the things that have contributed to our flattening of our curve. So now if we look at Sub-Saharan Africa, we see a similar sort of trend, but I would argue that whereas in the United States, maybe you would look at that as an encouraging plot, in Sub-Saharan Africa, it's maybe discouraging, because it's most likely not that there's been widely adopted energy efficiency measures that have reduced per person consumption. It's most likely the fact that there's been an underinvestment in electrical infrastructure that it just hasn't kept pace with the population. So as the population rapidly grows across many countries in Sub-Saharan Africa, the per person use is going to drop unless you invest in new power plants and transmission lines and so forth. So let's go from a macro scale down to a micro scale. Let's look at the actual rural communities. So these communities that I'm going to talk about are going to be off-grid, and they're what I would say maybe typical off-grid communities, although every community, of course, is going to be different. So if you look at a rural community, you can really take their energy needs and you can split it into 3 categories: the energy used by the households, the energy used for community services, and then the energy needed for productive uses. So let's look at each of these in some detail here. So a good question to ask is, how much energy does a typical household need? And if we look at electricity, the answer to that question really depends on what you're trying to do? What level of service are you trying to provide with that electricity? Now, some estimates for an individual person range between 20 to 100 kilowatt hours per person per year. And this is actually a very modest amount. That's less than 1 kilowatt hour per day. Other estimates that try to account for the size of a household will put it more like a 1 kilowatt hour per household per day. So you get that sort of, between these two measures, you get sort of a sense of the amount of electricity that you would need to provide. Now, if you look at a village then with hundreds or thousands of people, you'll quickly see that this is actually, it ends up being a very expensive off-grid system if you want to provide this amount of electricity to everyone in that community. So another way of looking at it is trying to map the service you want to provide with the power level of that service. So for example, if you're only interested in providing basic lighting, then you can get by with a very low power system. It doesn't need to be very complicated. It doesn't need to have a high power rating. But as you add services or increase services, we go down each row here. You can see that service, as the service increases, so does the power consumption. So we start with lighting, and then we go into communication and entertainment, where we might have TVs and maybe computers. Those are still fairly low power devices. But once we start getting into space heating and cooling, refrigeration, mechanical loads, then the power amount increases. So if you're thinking of an off-grid electricity program, you quickly see that there's going to be a limitation, at least unless you have an unlimited budget, where you need to decide, are we just doing lighting and communication and entertainment, or are we going to be focusing on, or at least allowing for productive uses, mechanical loads, etc. And that's really going to dictate the approach to electrification that you take. It's what level of service you're targeting. And I'll argue that you don't need to provide full service to people in these rural areas to have a meaningful impact on their lives. You don't need to replicate the grid in order to have an impact. Even lighting, TV, radios, you can make a big difference in somebody's life just targeting that lower end service. So if we look at the energy needs of a household, depending on where the person lives and a few other assumptions, the requirements are somewhere between 5 to 15 gigajoules per person per year. And this isn't just electricity, this is just energy. Like the typical energy requirement is between 5 and 15 gigajoules. Now we can compare that to the the global average of 80, and you can see that there is a difference there, right? It's not an equal distribution there. We have quite a difference between the global average and then what people in rural areas consume. And I think it's unrealistic then to actually provide 15 gigajoules of electricity to each person in a rural area. It would take a very, very large system to be able to do that. So then we would usually target some of those lower services that can't be easily replicated with traditional fuels. We would look at providing electricity for phones and lighting and so forth. Let's move on to talk about community services next. So here we're looking at the energy needs of say churches or schools or health posts. And if we look at what we use electricity for in schools in rural areas when they get it, it's usually for internet, telecommunications, computers, ITC, and also enhanced teaching technologies like projectors, digital cameras, printers, and so forth. Healthcare facilities, we use electricity for lighting, again, ITC. Refrigeration of vaccines and medicine is quite important. Suction machines, diagnostic equipment, and also to create hot and clean water. And if you're designing a system for a health post or a healthcare facility, the electricity you provide needs to be reliable. So you would take that into account when you design your system. And then finally, we'll talk about productive uses. Productive uses are really important and because they help the economic sustainability of the system. So the typical productive uses that we see in rural areas are for pumping water, for milling maize, for processing agricultural and forest products, small appliances like shavers and televisions, refrigeration, brick making, and sewing. These are the types of productive uses that you typically see for electricity. What you see here actually is a picture I took in Zambia, and inside that blue house is a machine that mills maize that the people in the community collect. And so it's a fairly large off-grid system, but that's what it does. It provides a lot of benefit for that local community to be able to mill the grain locally and without having to buy, say, petrol for their hammer mill. So when you think about doing an off-grid program, you would, again, want to know what the energy needs of that community are, the domestic, the community service, and the productive use needs. And then you would map that to an electrification approach. And you can think of the technological approaches to electrification as lying across a continuum, where on one end we have low expense but low service products like solar lanterns that might provide just a few LEDs of light, maybe recharge a cell phone. And then as we move across this continuum, we get into larger off-grid systems like solar home systems, which now can power several lights and TVs and fans and radios. And then we get into energy kiosks where we now can power freezers and pumps and things like that. And then we get to mini grids, which more or less replicate what you would get by being connected to the national grid. In fact, many mini grids offer higher reliability and service than national grids in many countries. There's a report that came out in July called the State of the Global Mini Grids Market Report. And if you go to minigrids.org, you can access it, but it contains a lot of information about mini grids. So if you're interested in mini grids, I would encourage you to check out that report. But a few things I'd like to point out from that report are the cost of electricity for solar hybrid mini grids, and being somewhere between 49 and 68 cents per kilowatt hour, and I think that's US dollars. And so that means that the electricity is going to be expensive. This is maybe 4 or 5 times what I pay in my home in the United States per kilowatt hour. So make no mistake about it, when you provide electricity from an off-grid system, it's usually going to be more expensive than the grid. In fact, almost always. And actually one reason why is that off-grid systems generally don't get subsidies. They're not subsidized like many countries subsidize their electricity tariffs. So it's not a cheap thing to do, which means you need to find the right community that can afford that electricity, afford to pay it. Now, the other thing I want to point out is the potential for mini grids in sub-Saharan Africa and South Asia. Over 111 million households could realistically be served by these systems. So maybe you're thinking about being an entrepreneur. There is a big market for it, and the pieces are coming into place for it to be viable. We're going to transition now and talk about some of the more technical aspects of off-grid systems before I talk about two simple case studies. And most of my talk from here on out is going to focus on larger systems like mini grids and energy kiosks, rather than solar home systems or solar lanterns. So if we think of a mini grid, we really can split it into 3 subsystems. We have the energy production system, the distribution system, and the end use system. And they're all going to have different components as shown here on this slide. And I'm really going to focus on the energy production system, although of course you wouldn't ignore the design of the distribution system and the end use system. So if we look at that energy production system, we're going to have some basic building blocks that we'll use. We'll have the energy conversion technologies. We usually will have energy storage. There's going to be some converters, some controllers, and then at least some local load that we're going to supply. So here's the architecture of a typical off-grid solar system. And in it, we will have a PV array. It might just be one module, but it could be several modules connected together. Solar arrays put out DC natively. We'll connect the PV output to the DC bus via a charge controller. And this charge controller usually has two important features. One, it has what we call a maximum power point tracker, which ensures that the PV array operates at its maximum power point. And the second thing that it does is it's going to prevent the battery from being overcharged. And so what it's doing is it's constantly monitoring the voltage on the DC bus, which is the battery voltage. And as the battery voltage starts to rise when the battery charges, it's going to reduce the power from the PV array so that we don't over voltage and damage our battery or shorten its life. Now, the charge controller itself, you can think of as just a DC to DC converter with just some special logic to achieve those two functions, the maximum power point tracking and the overcharge protection on the battery. Now, most off-grid systems have AC load, at least larger systems like an energy kiosk or a mini grid. And that's really because it's far easier to get larger power appliances that are AC powered versus DC powered. So although there are some DC only mini grids out there, it's really only used then for lighting and maybe powering televisions, not larger loads. So then we would need an inverter then to connect any AC load that we have. We can have systems that are more complicated. We can introduce, for example, a generator. So here we have like a petrol generator. And there's a couple of different ways of doing this now. We can connect it to an AC bus, essentially through a transfer switch, so that we provide our AC load either by the inverter or through the generator set. But nowadays, the inverters, you can get inverters where you would connect the generator directly to them, and the generator can actually be used to charge the battery. So it would have a bidirectional flow of power through the inverter if you choose it. And then the inverter and the genset could work together to provide a load. So you see actually quite a few hybrid systems that are out there. Hybrid systems, I think, are really a good choice if you have a couple of days or weeks a year where you don't think you're going to have enough sunlight, or there might be some time during the year where the load is extremely high for a short period of time, or you desire high reliability. It's probably cheaper to have a genset that is only run a couple of hours a year than to oversize your battery and PV array to try to do it all with solar. So the energy conversion technologies that we see used in off-grid systems are usually gensets, and they might be powered by biomass, though that's kind of rare. Solar, wind, or hydro turbines. These are the ones that you would typically see. You wouldn't see geothermal or tidal or some of the more arcane or archaic systems there. You would typically just see these four. And here's just some pictures of what those look like in the field. On the upper left, you see different gensets of different sizes. The one with the yellow top is just a portable genset that you can move from house to house if you'd like. And on the right is a larger one. This is a few hundred kilowatts in size, and it's pad mounted for a mini grid in Haiti. On the right, you see a wind energy conversion system. This is just a small wind turbine. And on the bottom right, you see some of the different types of hydro turbines that you might see, like a Pelton or a crossflow turbine. So here's what an off-grid system actually looks like. You can see the different controllers and some of the components here. So this is a hybrid system that uses solar and wind. And because wind turbines output AC, you need to have rectifiers to convert them to DC, and that's what's shown up at the top. We have a diversion load controller, which is like a charge controller, but you use it for wind. And instead of open circuiting the wind turbine, you take the power from the wind turbine and you shunt it to a diversion load. And these are just big resistors that you can kind of see in the picture here. The PV arrays are connected to the system through each part of the array has its own charge controller, and then this big blue box here is is the inverter. Now, the control components are going to look different depending on the size of the system. On the left, we see it for a very large mini grid. I think this might be around 60 kVA in size, and up at the top is for one where it's maybe 600 VA in size. But they're going to have the similar components. They're usually going to have a charge controller and an inverter at the very least. Here are pictures of battery banks. On the left is a 48 volt system. We have 6 volt batteries connected in series. And as the systems get larger and larger, you will use lower voltage, and you'll put more batteries in series and fewer in parallel. We want to avoid parallel strings, usually for just safety reasons. You don't want to have a string fail and then have all these other parallel strings discharge into it. So batteries can take up a whole room even, depending on the size of the system, as shown here on the right. Okay, now I'm going to talk about implementing some of these systems and my experiences in doing them. So if you're thinking about doing an off-grid program, I would say that there's 8 steps that you're going to follow. There's prospecting and screening, site assessment, some decisions that you'll make, technical and commercial design. Then you'll go through pre-implementation, implementation. You'll arrive at an ongoing operation stage, and then finally you'll make some decisions on whether to expand or retire your system. So I'll go through these briefly, and I'll highlight some of the more important parts. So in the first part here, what you're trying to do is you're trying to decide which community to have your electricity access program in. And there are thousands and thousands of communities that really could use an off-grid system. So what you're trying to do here is to try to take the list of communities and narrow it down based upon some factors like distance from the existing grid, the availability of solar resource, or maybe some demographics. And there's actually quite a few tools now online that will help you screen whole countries even to find communities that might meet your criteria. On the right are some screenshots from something called the Electrification Pathways tool that's online, and there's several countries, including Zambia, that it has in its database. So once you've identified a few communities that you think that the electricity access program will be viable in, you need to go there. You can't just do it from your office. You need to actually visit the community and meet with local officials and really confirm that the data you got in step 1 is reasonable, because there can be errors, it could be old data and so forth. And here you might actually start taking measurements of sunlight or wind speed, and you would also be scoping the area to see where you might put distribution lines or your powerhouse and so forth. So now you've started investing heavily in the community because you've mobilized and you've gone there. Now in step 3, you look at the communities that you visited and you try to decide which one, or maybe several of them, which ones are worth committing to. And so how you decide is going to depend on your goals as an organization. Are you trying to maximize input or impact? Are you trying to make as much money as possible? And there's several tools that you can use to help make that decision. Pestle analysis is one. Risk or decision matrices can be used. You can apply a theory of change framework to see which one will have the most appropriate impact and so forth. So some of the things that you would look for that would make a community attractive for electrification are: the national grid is far enough away that it won't be extended to your community. You look for a competition from other off-grid systems. You want to put your system in a place where the demand is going to be high and you expect people to use it in a productive way or to improve the quality of life. Because electricity from off-grid systems is expensive, you want to see that people are able to pay and are willing to pay for the electricity, otherwise your system really won't be sustainable. You want to make sure that you either have adequate sunlight or wind speed or a way to get fuel for your genset there. Dense populations generally make it more economical to do an off-grid system there. supporting infrastructure is helpful, like roads and a good cellular connection. You want that local community to have good political stability, to be well organized, and you'd be looking for communities where you think that there's low risk of theft and vandalism of the components, because that does in fact happen. In stage 4, what you're doing is the actual design of the system. And I'm not going to cover the design approaches in my talk here, but there's actually quite a few webinars that I've given that discuss this aspect. So if you do some searching or contact me, I can point you in the right direction. But you're designing the technical and commercial aspects of your off-grid system. And you usually do this in an iterative process. And sometimes you'll just decide that actually what you thought was going to be a community where you could install a good system, you might realize that it's just going to be too expensive and no one will be able to afford the electricity, and so you'll have to move on. However, and hopefully you find that you have a system design that seems to work, then you go through the pre-implementation stage. You might get permits, you would identify vendors to do the installation if you're not doing it yourself. You'll do procurement, and you'll do some community outreach where you want to identify specific customers, and then you'll have to sensitize them to the program. So what their payment is, how much different appliances will use, and so forth. The implementation is when you actually construct the system. And this usually can be done quite quickly, just in a matter of days, depending on the scale. And then you'll do commissioning and verification. And then at this point, your system is up and running, and you're serving your users. You should have a maintenance and repair program in place. You should be collecting technical data on the system to help you design systems in the future, collecting commercial data, and then hopefully you're collecting social data to measure the impact and to see what good you're doing and maybe areas that you can do better for your next system. And then finally, we get to expansion or retirement. And in here, this is something that we need to think about at the outset. You know, everything that you'll install will eventually fail, and you'll have to make some decisions on how you're going to repair it, or if you want to retire the system. Maybe the system isn't working the way you expected it. Maybe the users aren't consuming much electricity. Maybe they're not able to afford it. Who knows? But you need to be prepared to return the land and the environment to the original condition. You need to be able to dispose or recycle the batteries or equipment. And then you'll need to have some sort of community relations to maybe make sure the community understands why you're decommissioning the system. Now, I have pictures here where we had a system in Kenya that we decided to decommission. You can see the batteries being removed. What actually had happened is the batteries had reached the end of their life cycle around the same time the grid was extended to the community. So we decided what we were going to do, instead of rehabilitating or replacing the batteries, we simply connected the system to the grid. And that turned out to be far more economical and really the way to go. So not all retirements are a bad thing. Now, if you aren't retiring your system, at some point you might need to expand it. Maybe it's so successful that there's going to be additional users that want to use it. And so you should think about ways that you can do that, either serving more customers or improving the amount of electricity that's available to your users. So I think I'm going to go quickly through this. One of the first questions that you'll have to answer when you do an off-grid system is what type of technology to use. And the default is solar, and that's usually a good default to go to, but there are a lot of other options that you might consider if you think, for example, you have a good wind resource or hydro resource. But for each type of conversion, energy conversion technology you might use, there's a number of factors that you would want to consider. Importantly, think about the repair, replacement, and maintenance. Failing to think about that at the outset of a system implementation is, I think, a big mistake. Remember, everything fails, everything requires maintenance, and you need to have a plan to replace and repair. Okay, I'll conclude here with some system examples. One that we implemented a year ago and one that we're implementing right now. So this is a map of Zambia, And most of our projects now are in the southern province, which is by sort of Lake Kariba. So we're an organization from the United States, and we don't suppose that we know Zambian communities that well. So we partner with organizations in country, and we've been working with Caritas Monze, who's been involved in the southern province for over 50 years doing different types of development work. So our model is we rely on our local partner to outreach to the communities, to identify communities for us. So that's really, steps 1 and 2 of that 8-step implementation project. We have our partner really do that. And then we'll participate in visiting the communities for the site assessment. The community itself is, so this is the community of Cheba, and this is the women's group. And our model is that we want local ownership of the system. So we don't actually own the systems. We essentially gift them to our partner and community. And so there has to be an organization structure. There has to be some group that's going to take ownership of it and operate it and maintain it. And in Cheba, it was a women's group, as you can see here. And Cheba is on the Kafue River here, and we put the kiosk sort of in the center of town, where it's most densely populated. And so we did some assessment trips where we went and visited Cheba. We did surveys, we did focus groups, and we got an understanding of their resources and wants and needs there. So here are just some pictures. You should always do some demographic surveys to get an idea of the community, and so you can design the system accordingly. And I'll actually note on this slide, we did surveys before we did the project, and then while we did the project. And although some data are consistent, some actually turned out to not be as consistent as shown here on this slide. So when we did the assessment, we asked several questions. For example, how much time a child would spend gathering water. And during the assessment, it was 9 hours a week. And then during the implementation, it was only 2.5. So obviously, there's some questions that come from this. And what I'm trying to say here is, although these are good questions to ask, the reliability of surveys in general is, in my experience, quite low. So you should never, as we would say in the US, you should take it with a grain of salt. There's always going to be some opportunity for bias or misinterpretation in your results. So let's look at some pictures of these systems as I wrap up here. So this is what the system in Cheba looks like. You can see there's 3 rows of solar panels, so there's 9 panels total mounted on the outside. We also wired security lights, which are important to do. This is what the electrical system on the inside looks like. So we have our batteries down below, we have our charge controller, we have our inverter, we have some battery monitoring equipment, and we have a data acquisition system here, which I'll talk about briefly in a moment. So in Cheba, it was almost a 3 kilowatt system. It's a 48 volt lead carbon battery. We decided we were going to try lead carbon batteries to improve the life cycle. I can talk about that more if you have questions about it. And this solar kiosk is providing really powering freezers for a small store to sell, to freeze meat and sell cold drinks. It's powering lights, and it's powering sewing machines, phone chargers, and hair clippers. So here's just some pictures of what the women's group wanted. They wanted sewing machines to make and repair clothing. You can see the freezers back there. The data acquisition system that we install helps us measure and record in real time the technical performance of the system. And so here's just from a 2-day period, we can look at the power coming from the solar array. We can look at the different temperatures in the freezers, for example, to help us tell if they're on or off. and we can look at the battery voltage profile. And there is a bit of an art to interpreting all of this. And again, I've given webinars and I cover it in my book, how you can look at a profile like this battery voltage and tell if it's your battery is healthy or if you can add more load to your system. For the CHEBA system, this is our typical load profile, which is really important to see how much power is being used at night and then how it's being used throughout the day and so forth. So when we collect this data, it's helpful for us to understand how it's being used, but almost more important is that it helps us understand how we should design our next system. So instead of just asking questions and trying to guess when certain appliances are going to be used, now we have data from a similar system, and we can use that then to design our next system. So this is what CHEBA looks like at night, and they have a little projector here, and they're showing a video to the children. The project that we're working on now is in Kinshomba, and we are in the pre-implementation stage of it. So stage 5, I think, or stage 6. And Kinshomba is another off-grid community in Zambia, and we're working with Caritas as our local partner, but the system's going to be operated by the Chikuni Youth Agricultural Training Center, where there's about 40 young adults that are going to be working the system. We did our surveys and our assessment, and the community really was interested in having this pump powered by solar power to also use for irrigation in addition to water. So that's one of the aspects that we're doing. We did a rendering of what the kiosk is going to look like because they hadn't had that structure built, and the community wanted to have a small office, hair salon, and barbershop, as well as some a room for incubating chickens and a shower facility. So we designed the system based upon the community's needs and, of course, our budget. And this is a picture of what the system's going to be powering. We also have some fans there to help cool batteries and move the rejected heat from the freezers so that the kiosk doesn't get too hot. This is going to be a large system, over 5 kilowatts of power with an 8 kilowatt inverter. And the battery, although it says AGM here, it's actually going to be a lithium ion battery that we're building. So our organization, it's volunteer run, but our volunteers are practicing engineers. So we produce diagrams like this, and we have Zambian companies that actually bid to supply and install the systems for us. So we very much support capacity building. We don't go and do it ourselves. We have local companies that do it for us. And so you can just see pictures of the kiosk being installed here. We expect within the month to have the electrical system put in as well. And here is some pumping that, borehole testing that they did to size the solar pump that we're going to use for the water pump. So just to conclude then, there's about 1 billion people that lack access to electricity around the world. And off-grid systems are viable in providing access to electricity, but it needs to be done carefully. You need to do it in a way that couples productive uses like refrigeration or water pumping, etc., so that the system can be financially sustainable. Remember, it's expensive to provide electricity in off-grid systems, and so anything you can do to spur economic activity, you can take some of that revenue and set it aside to replace parts, replace batteries, and so forth. You really need to be looking for those opportunities to do that. And then in my experience, local partnerships and community engagement are really fundamental to any program's success. So you can't be an outsider going into this community and imposing your will. You really need to listen and work with them to figure out what works best. So here is my contact information and my email and Twitter handle, and I think that's all I have. So I guess it's time for questions, maybe.
No, thank you, Prof. Henry.
Yeah.
First class, thank you. We'll go to questions. I'll bring back the screen. Thank you. David, you're going to help me with questions. Let's start first. I'll start with the last one and then work myself towards the other questions. One from Ricardo. Seems to me that the most sensible way to use microgrids would be to sponsor one in an area with high potential of growth in order to reach a threshold after which the community becomes financially able to afford a connection to the national grid. He says, Ricardo says we need to plant the seed and then recoup that expenditure later. Your comments on that, David and Prof. Henry?
David, would you like, I can say my thoughts, but I'll let you go first.
You can go for it, Henry. Thank you.
Okay, thanks. Well, it's certainly an interesting idea. I mean, in a way, we like to think of at least our off-grid systems as being catalysts to spur economic growth. I think, though, many of these communities, almost no matter how prosperous they are, if they're far away from the grid won't be coming anytime soon. And that's an unfortunate reality, is even if the community is well off and could afford to pay the hundreds or even in some places, $1,000 to connect a home, there's a lot of distribution lines that the state utility might have to install just to get to that community. Alternatively, you could target communities that are somewhat close to the grid and hope that the grid will come to them once they can demonstrate that they are consistent users of electricity. I don't know that I've seen that happen very often. And you also have to think about the assets that you have in place. If you're doing this as a for-profit enterprise, what happens when the grid comes there? You've invested tens of thousands of dollars perhaps in batteries. What do you do with those? So those would be some things that I would think about with that idea.
Yeah, certainly, Henry, that sounds right. And as you mentioned during your presentation, the size of the community and the prospective need over the medium to long term comes into play. So, yeah.
Thank you. There's one from Mohammed to Henry. Why did you decide to use lithium-ion batteries over AGM?
Yeah, for a few reasons. Lithium-ion batteries, the costs are going down, and so the delta between lithium-ion and AGM was getting smaller. We noticed that in the field, the AGM batteries that we have used, we've really been underwhelmed with how long that they've been lasting. If you look at the spec sheet from the manufacturer, you might expect them to last 5 or 6 years. We were finding that they might last 3 years or something like that. So a bit of it was a large motivator was hoping to get an improved cycle life out of them, but we also wanted to gain some experience in them. So we collect lots of data from our systems, and so we have now deployed flooded lead acid, AGM, lead carbon, and now lithium-ion batteries, and we're still learning. I mean, we might find out that the lithium-ion batteries are too temperature sensitive to really get that long life out of them, but we'll see. So yeah, I mean, I guess we're optimistic that we'll get a longer cycle life, but at the very least, we want to learn from their deployment.
Oh, thank you. There's one from Ludwig. He's very excited. What are the requirements to partner up with the organization? So Ludwig wants to come and join you.
Yeah. I mean, so we're a volunteer organization, and we're based out of Seattle, Washington, in the United States. And most of our volunteers are from that area because we do, well, before COVID, we would meet face to face and we would do our designs. We've had sort of mixed success with people volunteering with us from abroad, but that doesn't mean that it can't be done. It just means that we have to find very specific ways, well-scoped ways for somebody to be involved. We're always looking for people that are interested, people that might have connections to different communities, people that might have expertise, particularly on the data acquisition side of things, because actually a good amount of that is programming our dashboard and working with our databases on that. And we actually do have a research component. So researchers that are interested in off-grid work that might have data or some ideas, we could be a way of field testing some of that. So there are some ways that you can be involved with us remotely.
Yeah, thank you. So Ludwig, you're welcome. One from
Just
Thabo.
to add on to that,
Sorry,
just to add on to
carry
that,
on.
thanks. We had a project here in Cape Town a few years ago, and I was relating now quite closely to the content of Henry's presentation around the quality of survey, what you get from it, as well as whether or not to decommission a site after a number of years. So our project had to do with, in collaboration with the University of Cape Town, we transformed a shack that was built out of corrugated iron sheets to a structure built with brick. And the IEEE project that I led at the time had to do with providing access to electricity for that specific building. It was an orphanage with about 50 odd orphans, and through IEEE PES and a couple of our partners in Europe, including Crossing Borders, Stuttgart, and local companies such as MLT Inverters, we were able to set up a 3 kilowatt system, which worked for a number of years. But as Henry has indicated, you have to go through a monitoring and evaluation process, which sometimes is continuous. And what we found was that once they had access to electricity from this renewable energy system, the appetite for energy skyrocketed. And as a result of that, they had constant trippings. And then the project team would get calls every now and then, sometimes in the evening, to say, hang on, David and your IEEE team, why are we having this power trips and all that? So we had to explain to them that electricity is literally, access to electricity is not unlimited, in the sense that there are constraints to how you use energy. And the next step was then to engage in an educational exercise, educating the community on what it means to switch on 3 electrical stove plates at the same time, and what it means to switch that on with your kettle and other heavy electrical appliances. So I'm quite interested in the outcome of the work that Henry has done, because within the South African context, there is opportunity to have this sort of projects in some communities, but the educational aspect becomes very key in the sustainability of the project. Henry?
Yeah, I mean, I think your experience is one that many others have had, and I think it actually goes one or two ways, where you provide access to electricity, and if you charge people a tariff to use it, then often they use far less than you would expect. But if it's free, they will often use far more than you had anticipated. And you have to keep in mind that many people who gain access to electricity are really unfamiliar. And in fact, many people that aren't engineers are really unfamiliar with how much power it takes to heat a kettle of water versus recharge a cell phone. To them, there might be no difference in their mind. So certainly you do need to do some training, some educational pieces. And I think successful programs do that. I mean, we work with our partner to do that. We also do some training ourselves while we're there. And also managing the expectations at the outset seems to help. Early on, we would go to communities to do a site assessment. And despite me saying, not trying to commit to anything and really trying to manage expectations, somehow the message was that everyone was going to get free TVs and be able to use as much electricity for free as possible, as they ever would want. And so that message gets out, even if that's not the message that you want to send. And so you repeatedly have to convey that we're going to do this system. There's going to be limitations to what it's going to be able to provide, and really make that known. It's important.
No, thank you. Good conversation. There's one from Tabo. Tabo's interested in the cost comparison, average cost comparison between wind and solar PV systems.
Mm-hmm.
Your thoughts on that in terms of energy delivered?
Sure. Well, you're probably not going to like my answer because the answer is it depends, right? You know, a kilowatt of solar versus a kilowatt of wind, the solar nowadays is probably much cheaper. I mean, our latest bids in Zambia were about 65 cents a watt. Now, but of course, you don't compare things on capacity basis if it's renewable, right? You really need to know the capacity factor, and to know the capacity factor, you need to know the quality of the resource. So certainly there's going to be some parts of the world where it's windy enough where you can put a wind turbine up and it's going to produce enough energy that it's cheaper than solar. But I think more and more you see solar and battery prices decrease, and I don't know that wind is really getting much cheaper. In addition, wind, it has not an insignificant maintenance component to it. So if you look at the total life cycle cost of wind, you know, there's fewer and fewer places where it's making sense. Now, 10 years ago, when I actually started, my entry point was wind turbines, and we built wind turbines in country, and we did all that. But it's a lot of work. Finding out where it's windy is a lot harder than finding out where it's sunny. Building towers, maintaining towers, it's a much more risky proposition than solar panels. So I always try to go into any community with an open mind as to what resource might work. But in sub-Saharan Africa, there's usually a lot of sunlight, and you usually get steered towards solar because it's probably going to make the most sense. I would say the two exceptions to that are if you have a good hydro resource in the area. Micro hydro power is fantastic. And in situations where a genset actually might make sense versus solar. Again, it depends on the application. If it's just a few hours of high power load, a genset might be better than a battery or a solar system with a battery.
Oh, thank you. So one from Paul Vermeulen. Paul wants to know about the time scale for calculating the cost of the electricity from an off-grid system. What time scale would you look at for the payback period?
Yeah, well, I mean, one approach would be to look at the component that you expect to last the longest, and that's generally the solar panels, right? So you might look at it for over a 20-year period. But I think that if you were to do that long of a period, you'd have to account for the fact that your batteries are going to fail every 3 years to 5 years if you're lucky, and then inverters might last 10 or 15 years, something like that. So these analyses, usually what you see is that they've done a levelized cost of energy analysis going out, anywhere from say 5 to 20 years, looking at the cost, and that's typically what you see. But like any forward-looking analysis, I mean, there's so many unknowns, right? There's so many unknowns. I mean, your inverter might fail the day after the warranty expires, just because it's a high ambient temperature, or who knows. And it's it's hard to design a specific program just off some average assumptions. You really don't know what the feature will hold.
Oh, thank you for that. There's one from colleague in Colombia, Maximiliano Buono. How difficult is it to adjust a financial plan for these types of projects? He talks about import fees, currency variations, etc. Any comments on that?
How to adjust the financial plans? Was that the question?
Yes, especially when you're looking at currency variation.
Yeah, it's really hard. The model that my organization has is, because we're a nonprofit, we're not ourselves going through a business plan on when we're going to recoup our investment. So we don't have to worry about that so much. But what we do is have to estimate the cost of our projects so that we raise and allocate the right amount of money. Certainly, currency risk is it can be a big factor. In Zambia, where we work, you know, the kwacha is going down against the dollar, so it's been favorable for us. But I would say, I guess, my advice about currency would be to know the community and know the country that you're working in really well. If you're just hopping around the globe trying to do a project here so you can put a pin in a map and a project there, they're probably not going to be that well. I mean, we know Zambia. We follow the news. We follow reports on how we expect their economy to do, and we, you know, build that into what we expect it's going to cost for us to do our projects. In addition, we have a good sense of what's going to be imported by a contractor and what will be done locally. So even though the kwacha might be depreciating against the dollar, we know that the equipment's going to be imported from, say, South Africa or Germany, and so that's the real cost that we're looking at, not the Zambian cost. I mean, it's not going to change that rapidly if they have to import the equipment anyway. But it is really challenging to do. Make no mistake about it. Coming up with a business plan that makes sense is hard to do, and it's easier to get it wrong than it is to get it right.
Thank you for that. We have another one from Paul Vermeulen. Paul says that most people still use biomass for cooking, and he's basically looking for your comments. Is it cost of electricity or access to electricity that causes this scenario where people still use biomass for cooking?
Yeah, I think it's a little bit of both, and there's maybe even a third element, which would be cultural. So let me talk about each of those. So even in large cities, when I lived in Kitwe, Zambia, for example, it's very common for people to use charcoal to cook, even though they have an electric cooker inside their house. So there's a bit of a cultural reason for that. I mean, even here in the United States, we love to grill and barbecue. You know, we love to get charcoal and cook that way. The food just tastes different, and sometimes we like that. I think because cooking is so high power and energy hungry that we don't see systems designed. It's incredibly expensive to design a system for that power and energy requirement, especially if it's going to be done at night. So the capital costs can be prohibitive. And then of course that then follows through to the user, where the user then has to decide, is it more expensive to cook with my electricity or with wood that I might be able to get for free? So they're making that economic choice as well. So they, you know, a limit is getting a system that can support that to them. And then if that system is there, can they afford it? Now, there's some research that's being done right now in, I think, Tanzania, where they're looking at these pressure cookers and using that in these communities that are supposed to be extremely energy efficient. And we'll see how that goes. But people are pretty slow to abandon traditional ways of cooking. I mean, it's been cited as a source of failure for improved cook stove projects for a really, really long time. Switching technology, switching fuels is, even if it makes some economic sense and might even be more convenient, people like to cook in a traditional way, a way that they're familiar with.
Oh, thank you for that. There's one from Alan Paul. And given your experience with off-grid systems, what's your sort of average cost of energy delivered to date in US dollars per unit?
Oh, that really depends. You know, I think the values that I've shown, that I showed earlier in my presentation, are maybe on a bit higher side than what we've seen. I mean, it's certainly, we're in the range of more than 20 cents a kilowatt hour. But we don't sell our electricity by the kilowatt hour, right? In our systems, we don't. That's not our method. We provide it to these businesses, and they save some of the money to pay for replacement and maintenance. The other thing to think about in that calculation is there's a difference between what a system could produce and what it does produce. And what I mean by that is In some systems, the amount of energy that the solar panels could produce isn't being produced because the demand isn't there yet. So they're still ramping up, they're still growing into their full consumption. They have 2 freezers, not 3, and the system was designed for 3. So you have to ask yourself, well, what's a fair comparison? What was actually consumed or what could have been consumed? So there's a little bit of nuance to that. And then finally, I would say, I think our oldest system is about 6 years old now. And I don't know that that's enough time to really do a full life cycle cost of energy. But you're talking anyway at the ballpark at, 20 to 40, 50 cents a kilowatt hour. Somewhere in that range is where it's going to come in.
No, well done. Thank you. There's one from Jeffrey Nkunazi. In the data you've collected in sub-Saharan Africa, have you checked the correlation of electricity versus deforestation? Electricity usage versus deforestation?
No, that's something that I've looked at. I'm sure that people have looked at that. David talked about a study that he saw about some of the poverty impacts. I'm sure that people have done environmental impacts of if electricity is brought, does that actually reduce deforestation or degradation of forests? Because a lot of electricity access is just lighting and not cooking, my gut would tell me that it's probably not a strong correlation or a strong effect size for most of the systems that you see. Now, if the power lines come out, you have grid connection, subsidized grid connection that people can afford now, and people can get appliances, well, then maybe you would see that. But solar home systems, a lot of mini grids aren't replacing heating and cooking energy. Some are, but maybe not as much as you'd hope.
No, agreed. Ricardo's got one here. Have you experienced theft or vandalism of your solar systems? I doubt it.
No, we haven't, but that's a commonly reported and maybe a little overblown occurrence. I mean, I'm sure it happens. In fact, in some cases, it's vandalism where people will just decide to break the solar panels by throwing rocks at them, unfortunately. So some of the things that we do to try to prevent that is, of course, we try to install everything in a secure location. We always have bars and locks on the doors where the equipment is. We put solar panels on roofs. In some cases, the community will employ a watchman to make sure that nobody steals it. And we do what we can at the outset, and even before we started the project, to let the community know that it survives based upon them using it and taking care of it. And so there's a lot of social pressure that's built in then on not doing it. Now, the smaller systems, the products that you buy, these solar lanterns and solar home systems, I'm sure there's been some theft that's occurred. It's just easier to do. It's a little bit easier to do it discreetly than stealing a 350 watt solar panel.
No, thank you. Let's take one more. I see there's several more questions have come through. And
can I just quickly add,
David? Yes, please do.
Thanks, Pat. I just wanted to add 2 points quickly, Harry, on the theft and vandalism issue. So in one of the projects that I was involved with, it was the case that at some point, a few vandals made an attempt to, I would say out of sheer jealousy, as quoted from some of our colleagues on the project and myself. But the idea was that there was one community center that benefited immensely from the project, and there were members of that community, they were not too happy about it. And we had to decommission the site in the long run for multiple reasons. But yes, what we found was that good collaboration with the community members helps to preserve the legacy and objectives of the project, failing which things could easily go wrong. And then there was a question here by Brian Kamanzi, who is asking the question around, will the providers of off-grid connection be liable to subsidize by providing some form of free basic electricity. And that is on the back of what we have in South Africa, where below a certain income level, you qualify for 50 kilowatt hour per month as free basic electricity off the national grid. So with off-grid systems, will these service providers be in the position to offer such services? Henry, do you know if that has happened elsewhere in sub-Saharan Africa?
Maybe, but I'd be skeptical, and it would only really make sense if those off-grid providers themselves are being subsidized by the government. So in other words, they would be more or less acting like the government in doing that. Because you know, if you look at that example that you gave where it's 50 kilowatt hours a month, that's a lot. I mean, that's a lot to be giving for free. At least in the off-grid community context, many off-grid homes don't use anywhere near that if there's a cost associated with it. And if it's free, I don't think the economics would ever work out without another flow of cash to that mini grid provider.
Then the follow-up question from Brian then is it possible for government to subsidize those entities that provide off-grid systems? In essence, with this subsidy, they provide some free basic electricity off-grid, and that should hopefully drive the growth of these off-grid systems. Do you think that's possible?
Oh, I think it's possible. There's a lot of lobbying being done by the African Mini Grid Developers Association, which there are several locations, East Africa and I think West Africa too. It's just universally identified as a block to the proliferation of mini grids is the fact that grid connected customers get subsidies, but they're not being offered to mini grid customers. So it's like on the one hand, the government is favoring these people that happen to be connected by the electrical grid and not helping out people in the rural areas who arguably need more help, more assistance with the subsidy. It also makes it changes expectations because many people in rural communities have a cousin or they've been to the cities that do have electricity and they know what they pay per kilowatt hour. And then they'll look at their mini grid tariff and it's several times higher. You know, it's twice as much, 3 times as much. And then they think they're being ripped off, or then they'll decide that they don't want to pay, or they were only agreed to be connected because they asked their cousin who lives, you know, with a grid connection how much they pay and so forth under a different tariff, and not realizing that the mini grid electricity is more expensive. So then you have customers that are disappointed and disenfranchised and so forth. So I personally think that to the extent possible, it shouldn't matter. It should be agnostic whether or not your electricity comes from the grid or a mini grid. There should be if you're going to help one set of customers, you should help the other set of customers as well. And it's really being pushed on by some entities lobbied. Governments are being lobbied to include that in their regulations, and we'll see how much luck they have.
Sounds good.
No, thank you. Good conversation. Shall we take one more from Lutuli? Lutuli talks about migration. A lot of the folks from the rural communities are coming into the city now. So they're all coming for economic growth and prosperity, and they're coming to the city. Have you done any research on city scale off-grid and microgrid solutions, but for city application, for urban application? Very interesting concept from Lutuli.
Only indirectly, and not really addressing the migration issue directly. We did some research with my colleagues at Copperbelt University to see how people changed their electricity and actually energy consumption patterns when load shedding was started in 2015. And so we didn't look at the migration issue, but we did look at how people manage to change their electricity consumption in the cities when they didn't have reliable electricity. So these weren't mini grids that the people had, but essentially the wealthier people put in inverter, battery and inverter systems that charge the batteries during the day, and then or when they weren't load shed, and then used an inverter to power some of their households at night. And that actually would increase consumption in some sense because there's battery losses and so forth. Maybe, I don't know if David has done research on this urban question.
Over to you, David.
Not to that extent, but what I can definitely highlight is that from the pressure that municipalities see from the increased migration, even within this intra-country, the question is, existing municipal infrastructure as well as the grid, is it sufficient to cope with this increased influx in the medium to long term? In some instances, it's possible, but if you consider the distribution network and the transformers that are within the distribution network as an example, these transformers would have a finite amount of capacity to take on load, but with the injection of power from a mini grid, let's take an example, the University of Cape Town. We have a 1 megawatt system on our roof. It is possible to push this power into the grid through intelligent and efficient means, some of which we are currently working on. And how that is being sold back into the grid, or what the arrangement thereof is to recoup expenses over time, is definitely workable and will contribute to alleviating the stress placed on intra-country migration.
No, thank you. Thank you. We've just gone past the scheduled time of 6:30. I think let us take a conclusion at this point and say thank you to Professor Henry for his distinguished lecture this evening. There's still quite a few questions there, and we'll answer that and post it onto the website. And we'll continue the conversation in terms of how best we can all support and assist in alleviating energy poverty. David, can I request you say a last few words? Thank you. Over to you, David.
Thanks a lot, Pat, and to Henry for the presentation that you've delivered this evening, and the fantastic conversation we've had, the dialogue between our attendees and the host. Thanks to our partners, Southern African Power Pool, SIGRE, SAIEE, and the entire IEEE family and the University of Cape Town for bringing this to our audience tonight. Thanks a lot, Pat, for co-hosting, and we wish you all a pleasant day further, depending on where you are in the world. It's evening time, local time, South Africa. Thank you.
Thank you. Thank you, and bye-bye.
Thanks, bye.